Hello and welcome to this lecture 7 on the application of order ordinary differential equation, and in this lecture we are going to talk about orthogonal trajectories. As the name says, orthogonal we mean something at 90 degree, and trajectories we mean that curves. Okay, so the curves which cut each other at 90 degrees. Okay, so basically if you are given one family of curves and there is another family of curves, those curves cut each other at 90 degree, so we call them orthogonal trajectories. So orthogonal trajectories are two family of curves are said to be orthogonal if every member of either family cuts each member of other family at right angles. Okay, so if every member of one family of curve cuts the other family of curves exactly at right angle at every point, then we say that the two families are orthogonal to each other. For example, say you are given this family of straight lines passing through origin. Okay, so we know the equation of this: y is equal to mx. It's a one parameter family of straight lines. One parameter is m, okay, with the arbitrary constant, and x and y are variables. Okay, so for different values of m we will get straight lines passing through origin. So m1 y is equal to x, m2 y is equal to 2x, and so on. Okay, so these are infinite lines, straight lines passing through the origin, so we call it one parameter family of curves, and the curve is a straight line here passing through origin. So a family of straight line passing through origin, one parameter family of straight line, and one parameter because of one arbitrary constant present in this equation. Similarly, if we consider another family of curves which are circles with center at origin. Okay, so we know the equation of all these circles is x square plus y square equal to a square. With different value of a1, a2, a3 we get different radius. Okay, so say another family of curve, and it is again a one parameter family of curve because there is only one arbitrary constant a. Okay, so it's a family of circles through centered at origin. Now if we superimpose these straight lines on this circle, so that means we draw this family of curves and this family of curves in a single plot, then you see that the blue lines, they cut the red lines exactly at 90 degree at each point of intersection. Okay, so wherever the straight lines passing through origin meet the circle centered at origin, they intersect exactly at 90 degrees. So they are orthogonal to each other, and are called the orthogonal trajectories. So this family of straight lines passing through origin are orthogonal to the one parameter family of circles centered at origin. These two family of curves are orthogonal because the blue curves intersect red curves at right angles at all points of intersection. Okay, now the question is how to calculate this. Okay, if you are given one parameter of family of curves, say this, and then how to know that what are the orthogonal trajectories. So if you are given straight lines passing through origin, how we will know that this family of circles are the orthogonal trajectories, or the vice versa. If you are given this, then how do you know that these are orthogonal trajectories? So there is a set method, you can utilize that method to find the orthogonal trajectories for any given family of curves. The method says that say given a family of curves, so given this, say a function of x, y and arbitrary constant c1 equal to 0, so one parameter family of curves in Cartesian coordinates, and we want to know another set of family of curves which are orthogonal to this one. Okay, so your first step is that you formulate the differential equation which represent this family of curves. Okay, that means we are trying to calculate the slope of the curves. Okay, so your step one is that find the differential equation for the given family of curves by elimination of arbitrary constant. So this we have already discussed in the first lecture, and by taking one derivative of this equation and eliminating c1, we can calculate the differential equation whose general form is a function of x y dy by dx is equal to 0. Okay, so your step one is that from the given family of curve you construct its differential equation. Okay, now the second step is to know the differential equation for the orthogonal family. Okay, so given this family its differential equation, now we will from this differential equation we will calculate the differential equation for this orthogonal family. And the rule is that if the curves are orthogonal then their slopes are perpendicular. Okay, that means the slope of this differential equation and the slope of the orthogonal differential equation, their slopes product must be -1, so you will utilize that factor. Okay, so second step is that we calculate the differential equation of orthogonal trajectories, and because the curves are orthogonal then the product of their slopes at the point of intersection must be -1. So this slope dy by dx and the slope of orthogonal, the product must be -1. So using that we can calculate the differential equation for the orthogonal family and say that differential equation is some function of x y dy by dx equal to 0. So these two equations satisfies the relation that this slope dy by dx and this slope dy by dx, their product must be -1. Okay, and finally we calculate the solution of this. Okay, because this is the differential equation for orthogonal family, so if we solve this to find a solution, then that will be a family of curves and their family of curve will be orthogonal to the original family. So say this we get a function of x y and one arbitrary constant c2 say. Okay, so this equation is a family of curves orthogonal to the given family of curves. Say for example, say find the orthogonal trajectories to the family of parabolas y is equal to ax square. Okay, so with this is one parameter family of curves and the curves are parabolas here. When the a 1 2 3 so on, this y is equal to x square, y is equal to 2x square, y is equal to 3x square, so they are upward parabolas. And also if I take y a value as -1 -2 -3, so they are downward parabolas. So it's a family of curves of parabolas, upward and downward parabolas with one parameter a. So we want to find the what are the orthogonal trajectories to these parabolas. So what are the infinite curves which cut exactly at 90 degree to all these parabolas. So given this family of curves y is equal to ax square, our first step is to construct a differential equation for this. Okay, so we differentiate this one time and eliminate the constant a. Okay, so dy by dx is equal to 2 times ax, and then we can substitute a as y by x square here to find that the differential equation for the family of parabolas is dy by dx is equal to 2y by x. Now the differential equation for the orthogonal curves will satisfy that this slope multiplied the slope of that will be -1. So we can write the differential equation for the orthogonal family as dy by dx is equal to minus x over 2 times y. Okay, because this slope multiplied by this slope must be -1, so this product of this and this must be -1. Okay, so this is the differential equation for the orthogonal family. Or because slope product is -1, so I can replace this by minus dx by dy and then rearrange to find this. Okay, now once I know that this is the differential equation for the orthogonal family, I can solve this differential equation to find a solution that will be the orthogonal trajectories. So this is easily variable separable, so I can take 2y on this side dx and integrate both sides and add a constant of integration to find that x square plus 2y square is equal to c is the orthogonal family of curves to these parabolas. So these are nothing but ellipses. Okay, so if you draw these upward parabolas and downward parabolas, they are y is equal to ax square. And if I draw these ellipses x square plus 2y square equal to c, then you will find that they cut they cut the parabolas exactly at 90 degree everywhere. Okay, so these two set of equations are orthogonal to each other. Say I take one more example, that the electric lines of force of two opposite charges of the same strength at plus minus 1 0 are circles through these points of the form this. Find their equipotential lines, that is orthogonal trajectories. So again, given this one parameter family of circles x square plus y square minus ay is equal to 1, our first step is to find the differential equation for this family of circles. So we differentiate this with respect to x one time and then eliminate this a. Okay, so if we differentiate this one time, then it is 2x plus 2y dy by dx minus a dy by dx equal to 0, and then we can calculate a from here and substitute to find the differential equation for the given family of curve. So it's the differential equation for the given family of curve. Okay, so we calculated a and substituted it here. Now the second step is to write the differential equation for the orthogonal family, and because the slope dy by dx product is minus 1, so we can replace this dy by dx here with minus of dx by dy. Okay, and then rearrange this to write the orthogonal family differential equation. Okay, so here I've used dy by dx as minus dx by dy, and then just rearrange that to write this differential equation. Okay, now we can solve this differential equation to find the orthogonal curve. Okay, so is the differential equation in the form m dx plus n dy is equal to 0. So first we will check whether this is exact or not, and then we can solve. Okay, so m is x square minus y square minus 1 and n is 2xy. So we'll calculate m derivative y and n derivative x and see if they are equal or not. So m derivative y is minus 2y and n derivative x is 2y, so they are not equal. Okay, that means differential equation is not exact. Now to make the differential equation exact, we can try and see what is the integrating factor. So if we see that m derivative y minus n derivative x, it is minus of 4y, and divided by n, so 2y and 4y cancels out, so it's a function of x only. So here m derivative y minus n derivative x is the difference of this. Okay, divided by n derivative x. Oops, sorry, here it should be only n. Okay, is 2xy. Okay, this is not n derivative x, this should be only n, which is 2xy. So this difference divided by n is a function of x only, so we can find the integrating factor as integral e raised to power integral of this function dx. Okay, so integrating factor is e raised to power minus 2 by x dx integral. So it immediately gives us that 1 by x square is the integrating factor. A role of this is to make this differential equation exact by multiplying this equation with respect to this integrating factor. The integrating is this differential equation is rewritten as, okay, so 1 by x square is multiplied to this whole equation, so this can be written as 1 minus y square by x square minus 1 by x square dx plus 2y by x dy equal to 0. So now this is our new m, and there we have a new n. So m1 say is 1 minus y square by x square minus 1 by x square, and n1 is 2y by x. Okay, so again we will check derivative of m1 with y and derivative of n1 with x, and this time they are same. That means this new differential equation is exact. Okay, and so because this is exact, we can write the solution as integral of this m1 keeping y constant with the x, and only those terms of n1 which do not contain x. So there is only one term and it contains x. So second integral is 0 equal to constant. Okay, so we can integrate this with x. So we get x. Okay, y square is treated as constant, 1 by x square integral and minus 1 by x square integral. Okay, so this is the solution. Okay, we can just rewrite this. So this is the orthogonal family of curves to the given family. Now the next definition is the self-orthogonal. Okay, so orthogonal curves, they are intersecting at right degree. So self-orthogonal means the curves itself are intersecting at 90 degree. So a given family of curve is said to be self-orthogonal if its family of orthogonal trajectories is the same as the given family. Okay, so if you are given family of equation and if you calculate the orthogonal family, then you get the same equation. Okay, then that means those curves are self-orthogonal, they are cutting each other itself. Second definition is the orthogonal trajectories in polar curves. So the method is similar, that when the given curve is in polar form, the steps remain the same. That is, one formulates the differential equation for given curve, then find the differential equation for the orthogonal curves and find its solution curve. Okay, so the three steps that we used, the same steps are to be followed. Okay, slopes are to be substituted carefully. And say finally the isogonal trajectories. Okay, so isogonal means at a same angle. Okay, but that angle may not be 90 degree, that angle may be 30 degree, 45 degree. Okay, and so on. So two family of curves are said to be isogonal if every member of either family cuts each member of other family at a constant angle, say alpha. Okay, for orthogonality this alpha is 90 degree. Okay, and in general you can call it alpha, so we call it isogonal trajectories. And if m1 m2 are slopes of two family of curves at each point, then they are connected by this relation. So m1 minus m2 over 1 plus m1 m2 is tangent of alpha. If they are orthogonal, that means alpha is 90 degree, then obviously this denominator becomes 0. So m1 m2 becomes minus 1. So that relation we used in the previous examples. But if they are isogonal trajectories, then for any alpha this relation is true. Okay, so method remains the same for isogonal also. If you are given one family of curve, step 1 is you find its differential equation, and then use this relation with the given isogonal angle and slope of given family, and then we use the slope of the other family to find the differential equation for second, and then we integrate it to find the isogonal curves. Say for example, find the isogonal trajectories of the family of circles x square plus y square equal to a square which intersects at 45 degree. Okay, so given this family of circles centered at origin, we want to find the another family of curves which are cutting these circles at 45 degree. So the given equation is the one parameter family of circles. Step 1 is to construct the differential equation for this. So we differentiate this one time. Okay, so and differentiate with x. So 2x plus 2y dy by dx equal to 0. So immediately we have that dy by dx is minus x by y. So this is the differential equation for this family of circles. Okay, so it's the differential equation for the given curve. And say the slope is, say we call it m2. Now the slope of given family and the slope of isogonal trajectories, they are related by the equation we just said, m1 minus m2 over 1 plus m1 m2 is equal to tangent of alpha, and alpha is 45 degree, so that means tan 45 is 1. So basically the slopes are related by this relation here, and m2 is the slope of given, so m2 is dy by dx which is minus x over y, and m1 is the slope of the isogonal trajectories. So let us put m1 as dy by dx, the slope of isogonal trajectories, and m2 value from here as minus of x over y. So if we substitute m1 as dy by dx and m2 value from here, okay, as minus x over y, then this equation can be written as this differential equation, and this differential equation is the gives the slope of the isogonal trajectories to this circle. Okay, so now if we integrate this and find a solution of this, then the solution will be a one parameter family of curves isogonal to these circles. So we know that this is a homogeneous equation, so we can put y is equal to vx and then we can integrate. Okay, so y is vx, we know how to substitute this, solve this, separate the variables, and then integrate this to find a solution. Okay, and finally we have a solution, and back substitution v as y by x. So this is a family of curve, one parameter family of curve, and these curves cut these circles exactly at 45 degrees, so they are isogonal curves. This circle is isogonal to this one parameter family of curves. So this is about the orthogonal and isogonal trajectories. In the next lecture we will talk about higher order linear differential equations. Okay, keep learning. Have a good day.